Hello, everybody. This is Dr. Ekstrom, and welcome to the fourth of the seven video lectures to go with the November 1 workshop on creating content-based digital games on the structure and energy of matter. And we're going to continue our discussion of chemical bonding. But this time, instead of talking about ionic compounds, we're going to talk about compounds that break down into molecules. We call these covalent compounds. And so in covalent compounds, the bonds that atoms form are not based on electrostatic charges. Instead, what happens is that in a covalent bond, electrons are shared between two atoms. So basically what happens, we have two atoms that don't have completely filled outer shells or valence shells with electrons. And so in order to stabilize this situation, the atoms can come together and share their outer shell electrons, and in doing so create chemical bonds. And so in some compounds, we have equal sharing. So for instance, in the hydrogen molecule, we have two hydrogen atoms coming together and sharing their electrons across each other to form a chemical bond, and there's equal sharing. So the electron density is not shifted toward either one atom. They're both equal, and so we've got a bond between the two hydrogen atoms coming from this sharing. Now, there are some molecules where electrons are shared, but they are done so unequally. So, for example, in hydrogen fluoride, when a hydrogen atom and a fluorine atom come together, as they get closer together, their orbitals overlap, and enabling electrons to share. However, the electrons tend to be more attracted toward the fluorine atom than they do toward the hydrogen atom. This is unequal sharing, and it forms what we call a polar covalent bond, or most of the time we just call it a polar bond. And we can depict this in a number of ways. One of the more common is to put these partial charge symbols, so these little delta positive and delta negative symbols. It doesn't mean that we have ions formed, but it means that the electron density is shifted more toward whichever's listed, the atoms listed as partially negative. So in the case of HF, the electrons reside closer to the fluorine atom than they do the hydrogen atom, although technically they're still shared. So let's talk a little more about these polar bonds. So these polar bonds come about from unequal sharing of electrons between atoms in a molecule. So that means that there must be something about one atom, some quality or property that enables it to attract electrons more readily than the other atom does. So this kind of charge, there's a little bit of a charge separation that I mentioned before that we think of as partial positive, partial negative. But really the key question is, what is it about certain atoms that cause the formation of these polar bonds as opposed to the regular covalent bonds? Well, it turns out the key property is a combination of two properties we talked about in the first workshop. In the first workshop, we talked about some atomic properties that vary rather consistently according to position in the periodic table. We talked about ionization energy. We talked about electron affinity. How easily atoms can have or how easily electrons can leave atoms, or how much energy is released when electrons are added to atoms. The combination of these two properties is called electronegativity. And the result is, electronegativity we define as the ability of an atom in a molecule to attract shared electrons to itself. And so this is a property that varies rather consistently according to where an element is in the periodic table. So here's a chart, and it comes in handy when you need to know specific electronegativities. Most chemists use the Pauling 4-point scale for electronegativity, and electronegativities will increase going up a group and then from left to right in a row. And so that means the most electronegative element in the periodic table is fluorine. We don't count the noble gases, so all those helium, neon, and so forth. since they all have completely filled electrons and don't form very many compounds, we ignore those in the electronegativity table. So that makes fluorine the most electronegative atom, and it has a value of 4.0. So that's defined as part of the scale. As the electronegativity decreases, the value becomes lower. The least electronegative atoms in the periodic table are the ones in the lower left, so cesium and francium, and those values are 0.7. So these values are important because what we can look at are the differences in the electronegativities between atoms that are bonded together. That'll tell us what kind of bonds are going to be formed. So we have three situations that we can have. So when two atoms come together to form a bond, we can have equal sharing. So we have a covalent bond formed between identical atoms or atoms that have very similar electronegativities. We can have a polar bond form between atoms where there's unequal sharing. And then the extreme end would be the situation where electrons are not just unequally shared, but electrons are actually transferred from one atom to the other. And so basically these three situations are all in the same continuum. The last situation are, of course, ionic compounds, and we talked about those in the last video. So if we look at the electronegativity difference between two atoms that bond together, if that difference is very small, 0 to 0.4, then we say that's a covalent bond. We say the electrons are being equally shared. If the difference is larger, usually between 0.5 and 1.5, that means that we are going to have a polar bond. The atoms still form a covalent bond, but the electron sharing is not equal, and that's reflected in the larger difference in electronegativity. Finally, if the difference in electronegativities is over 0.15 between the two atoms, that's when we tend to have ionic bonds formed. There's no sharing. Instead, an electron or one or more electrons are completely transferred from one atom to the other. So, common exercise you can give students is give them a series of bonds and ask them to arrange them in order from the most to least polar. Now, in this set of examples, A and C are ones that can be solved just with a periodic table, whereas B, we probably need to actually calculate the electronegativity differences. Okay, so in the first example, the order is CF, NF, and OF. Now, the thing that all those bonds have in common are fluorine atoms. And so that, of course, is the most electronegative element in the table. And so the further away we get from fluorine, the bigger the electronegativity difference. So carbon and fluorine will have the largest electronegativity difference. Nitrogen and fluorine, the next biggest, and then the oxygen and fluorine bond will have the smallest difference. So that makes carbon-fluorine the most polar, then NF, and then the OF bond is the least polar. Now here, we have to, for B, we have to calculate the electronegativity differences to really get this right. And so silicon and fluorine, if we go back, let's go back. I'll show you how we do this. There we go. So silicon and fluorine. So the way we do this, fluorine is 4.0, silicon is 1.8. So that difference is going to be 2.2. Carbon has an electronegativity of 2.1, fluorine's 4.0, and so that difference is going to be 1.9. And do the same thing for the nitrogen and oxygen. It turns out this difference is going to be smaller than either of those two. And so we arrange the order. The most polar bond has the greatest difference in electronegativity. And then the smaller those differences, the less polar the bond becomes. And then finally, in C, here you can again, you probably can go in order. Boron is furthest to the left, and higher up than chlorine or sulfur is. You notice here in this set, again, chlorine is the common atom in all of them. So we can just compare positions in the periodic table. Boron is furthest away, so it's going to have the biggest electronegativity difference compared to chlorine. Sulfur is next, and of course the chlorine-chlorine bond is completely covalent. There's no electronegativity difference whatsoever, so that makes it the least polar. All right. Now, if we have a polar bond, we say, we talked about how we can represent that bond where there's unequal electron sharing. We can represent that by using these little partial negative and partial negative, partial positive charges, delta plus, delta minus. What that means is that a polar bond has what we call a dipole moment. A dipole moment means that one side of the bond has more electron density on it than the other. And so electron density kind of acts like a vector. And so we can use a dipole moment arrow to represent this bond polarity. And we have a little crosshatch at the base of the arrow, and then the arrow points toward the more negative side of the bond. And so here with this HF bond, we could use a dipole arrow to represent that polarity with the arrow pointing toward the fluorine atom. Now, the molecular, so then what we do when we put all the bonds together in a molecule is that if the sum of the bond dipoles point in a net direction, we can have a molecular dipole moment. So for example, for water has two bonds. They're both OH bonds, and both of them are polar. So we could say that the oxygen have a slightly negative charge, partial negative charge. The hydrogens have partial positive charges. Each bond would have a dipole pointing toward the oxygen. Well, what this results in is that as a molecule, the oxygen side of the molecule has more electron density than the hydrogen side. And so this gives the entire water molecule a dipole moment. And so we would say that water is a polar molecule. It's a polar substance. And this actually has effects. If you pour water into a graduated cylinder and take a look at the surface, at the top, you'll notice it's not completely flat. You'll notice that there's some curvature to it. And the curvature is due to attractive interactions between the water and the glass. It's trying to climb, the water's trying to climb up the sides of the glass because both silicon dioxide and water are polar substances. And so they attract one another. And we'll get into, in the next video, we'll start to talk more about interactions between different molecules, and it has to do with whether the substances are polar or nonpolar. Now, we can have situations where a molecule has polar bonds, but the molecule as a whole is nonpolar. And carbon dioxide is a great example of that. It has two bonds, both of them are CO, and if you look at the electronegativities, oxygen's 3.5 and carbon is 2.1. That's a large enough difference to make these bonds polar. But the thing is that you notice, so if we draw dipole arrows to represent this, the arrows are going to point toward the oxygens because the oxygens have more electron density, they're more electronegative. But you notice the arrows then go in the opposite direction. So the bond dipoles actually cancel each other out, making carbon dioxide a nonpolar substance. There's no molecular dipole, even though there are bond dipoles. So if the bond dipoles cancel each other out, the molecule will still be nonpolar. The last situation we have is when we have a nonpolar molecule because none of the bonds are polar. So methane is an example of that. Natural gas. Methane has a formula CH4, has 4 carbon-hydrogen bonds, and the electronegativity differences are only 0.4. So that makes all these bonds covalent, all equal sharing. There's no polar bonds, which means as a molecule, methane cannot be polar. So methane is also a nonpolar substance. Now, water is an interesting substance. And its polarity affects its properties. I've already talked about how it tends to kind of climb glass. If you pour water in a test tube or graduated cylinder, it tries to climb up the inside of the glass. And it's also the polarity that gives water the ability to dissolve a lot of ionic compounds. And so, you know, the table salt's very soluble in water. And what happens is that when we pour table salt in water, water molecules start interacting with the ions. And eventually, enough water, this interaction will become strong enough that the water molecules actually help the surface ions break away from the crystal, and then water molecules completely surround the ions. Here in this cartoon, you notice that we've got some water molecules surrounding a sodium ion that it's broken away from the crystal. And it's always the oxygen ends of the water molecules that are pointing toward the positive sodium ion. Okay, the oxygen end is the partial negative end. That's going to be attracted to the positive charge on the sodium ion. Now, when water molecules surround the chloride ions are negative, which means it's going to be the hydrogen sides of the water molecules that are attracted to it, because it's those hydrogens that have partial positive charges. So, uh, if the interaction between the water molecules and the ions are strong enough, then they will break the ions away from the crystal and dissolve the compound. Gives us our homogeneous mixture. If the if the ionic bonds in the crystal are stronger, then that particular compound will not dissolve in water. And there's lots of examples of that. But now, this kind of leads us into what kind of interactions can we have between different molecules and different substances that lead to some of their properties. So now from here we'll be getting into intermolecular interactions. See you then.